zeros. It depends on the non-zero that you're trying to, the level of the non-zero that you're trying to eliminate, and the level of the non-zero that is creating the fill-in. Okay, so in this example, we have, this is element A24. We have element A21, which is one we're trying to eliminate. And this fill-in is going to be created by element A14. Okay, so here, k is equal to 1, right? So these are initially have level 0, right, because they're original non-zeros. And we're going to update, this initially has level infinity, but we're going to update this level by adding these two levels together, 0 plus 0 plus 1. Okay, so this has level 1. And you can extend that process to see what the other levels are. We could actually do a more complicated example. Let me write that over here. So 6 by 6 matrix. It looks a little bit like a finite difference discretization. In fact, it is a very small one. Okay. We're going to eliminate this. This is going to create something over here that is of level 1, right? Just like before. And if we eliminate this one, we're going to create a non-zero over here of level 1. Maybe I should try to use some colors. Oops. OK. So now we've done the first column. Let's do the second column. We're going to eliminate this one. OK, that means adding a multiple of the second row, right? So here we have a level 0 and a level 1. We add them together, we get 1. Plus 1, we're going to get level 2. So this is going to be a level 2 fill-in. And over here, in the same elimination, a level 1, a level 0, and a level 0 plus 1, this is a level 1 fill-in. Okay, and similarly, we're going to get a 1 and a 2 over here. So if we say that we want a level 1 ILU factorization, then the pattern is going to be all of the level 0 entries, which correspond to the original entries, plus these extra ones that are marked 1. We're not going to allow any fill-in over here, which are level 2. Okay? And there's also a very nice way of seeing this if we look at, if we put in some values. Okay, so let's say we have all 1s on a diagonal. Okay, I'm going to draw the same matrix, but all 1s on a diagonal, and off diagonal non-zeros, I'm going to put epsilon, where epsilon is some small value less than 1. And this makes sense for many matrices from PDE discretizations, right? Because we have some form of diagonal dominance, right? And the off-diagonal entries are smaller in magnitude generally than the diagonal entries. Okay, this is if you look at your 5-point matrix, we have something that looks like this. Okay, now let's look at trying to eliminate this element. We need to add the appropriate multiple of the first row, and that multiple is epsilon. So we multiply the first row by epsilon, and we add it to the second row. Okay, so 1 plus epsilon squared is going to be just 1. We're going to drop the epsilon squared. Right, here's nothing. Epsilon squared plus 0, that's epsilon squared. Okay, and then these are nothing. So you can see that epsilon squared is smaller than epsilon, because epsilon is less than 1. Therefore, it makes sense to retain these level zeros before we decide to retain any level 1s. Okay. Now let's consider eliminating this guy by multiplying by the appropriate multiple of the first of this row, of the second row. That multiple is epsilon. So epsilon squared plus that, that's still 1. Epsilon cubed plus 0, that's epsilon cubed. Epsilon squared plus 0, that's epsilon squared. So you can see that this level 2 fill-in is proportional in our model to epsilon cubed, which is going to be much smaller than epsilon squared. Okay, so this is another motivation for defining levels in this way. And in particular, by adding, so these you can think of as being exponents, right, of the epsilons. Right, and this is the exponent of 1. Yeah.
Why are you keeping that infinity at the higher bound? Because as we can see, I mean, it is just acting as a upper limiter type thing. Right?
Yeah. There could be some very large value, not infinity. And we're going to take the min over here. By putting infinity here, then we can always do the min over here. The min is necessary because we're going to add an epsilon squared to the 1. That's just going to stay with the higher one, which is not changing the level. Okay, so there's also yet another very interesting connection to what we've talked about before. And that is the graph interpretation of level of fill. Let's say between I and j. And for here, because we've only been talking about symmetric graphs or symmetric matrices and their graphs, let's say we're going to assume symmetric matrix. And here, recall, we talked about something called a fill path. Right? A fill path between I and j is a path in the graph corresponding to sparse matrix between nodes I and j that only pass through vertices numbered less than I and j. Right? And if such a path exists, then there will be a fill-in. Right? So we know that for this thing, such a path will exist. And here's the really interesting thing. The level of I and j is equal to the number of edges on the shortest fill path minus 1. So the longer the fill path, the longer the shortest fill path, so there could be more than one fill path, but let's only talk about the shortest one. The longer that path means that more eliminations had to occur before that fill-in was created. Okay? The shorter the fill path, the fewer eliminations. Let's do the example that we did last time. which is this 4x4 mesh. Use a natural numbering. Okay. So there's a fill path between 10 and 12, and it is this one. And there are 4 edges. That's the shortest one. There are other ones, right? That's a longer fill path. But here's the shortest fill path. There are 4 edges on it. That means the level between 10 and 12 is equal to 3. Okay, can I use the screen now? All right, let me show you a few interesting things on MATLAB. So here's an interesting illustration of level of fill. So this is a sparse matrix coming from a 6x6 grid. Okay, so you should maybe recognize it very readily. And it corresponds to all of the level 0 elements, right? So we could do a Gaussian elimination with only retaining these non-zeros, and that would be called a level 0 ILU, or no-fill incomplete factorization. And now these red entries correspond to all of the level 1, right? They're fill-in, so they occur between the outer bands. And it's interesting to know where they are. They're like just inside of the next outer band. So if you were trying to say, well, what is a good pattern? And you want to decide which non-zeros to retain in the approximate factorization that will make your factorization accurate, yet use few non-zeros, then you might choose these. So that's level 1. And here's level 2. Okay, so they're colored in black. So it's the next layer in. How about level 3? So level 3 is kind of interesting. Some are hugging the diagonal and some are closer to the outside. So this is level 3. Level 4 in cyan. Okay. So they're coming in from both sides. Level 5. Which color is that? What happened with level 5? I know the level 6, the last one, is this yellow one over here. So now everything has filled in. You want to see that again? See what happened to level 5? So level 0, 1, 2, 3, 4, 5. Okay, 5 was cyan, and 6. So 5 was these light blue ones. Okay. And so that gives you an idea, not from the graph, from the matrix point of view, what things look like. Okay. Any questions about this? Okay, so let me show you how you're going to use this on the first assignment. So the first assignment is now posted on the course website, and you can download it. And it will be due in a week on Friday, although we don't have class on Friday, so I don't know how you want to collect the assignments.
But we will have
We'll have the workshop on Friday,
yeah.
and I assume that you're attending. Are you forcing them to attend?
Maybe I
Okay, so we'll decide later, but somehow we're going to figure out how to collect the assignments from you on Friday. Okay, so this is the same differential equation that we saw last time. Okay, and I think in our very first class. So do we have a pointer? Oh, thanks. Thank you. Okay, so same differential equation as last time. And on the course website, there's also this matconvdiff.m that you can use to generate the matrix corresponding to the finite difference using standard differences discretization of this convection diffusion equation. Just the matrix corresponding to the left-hand side. Okay? And there's an interesting way of treating the convection terms if you use the product rule for derivatives. Okay, so instead of discretizing this using calculus like I showed you last time, using the definition of a derivative last time, if we apply the product rule first, okay, then we only have this one derivative left, and we just discretize that one derivative. That doesn't involve exponentials at all. Okay, so in fact, it looks a little bit easier than the previous discretization. So the question is, well, we have these two different discretizations. Which one is better? I have no idea. So the report is to try to understand what are the differences between these two discretizations from different points of view. Okay, so the first thing to try is just to take the existing function and modify it to use a new discretization. Okay, and by the way, there are 4 questions here, and you should just write a short report to answer these 4 questions. Okay, and please use figures and tables so that we can see your results clearly. So the first question is, well, which discretization is more accurate? And to try to answer that question, let's just try to solve the differential equation for a solution that we already know. Okay, so if you choose this solution, you can integrate this twice for the right-hand side, right? To get the right-hand side, that will give you the solution. And then try to solve for different values of the mesh parameter and different values of the convection parameter beta. Okay? And for this question, just use the MATLAB direct solve. And you can plot, for instance, the error and see if one has greater error than the other. One discretization has greater error than the other. Okay? So besides the accuracy, the different discretizations lead to different linear systems, different matrices, and some of these matrices could be easier to solve or harder to solve by iterative methods. Okay, so here we're going to use ILU0 and BiCG stab. So use ILU0 as a preconditioner to BiCG stab and do that in MATLAB. Okay, and then question 4 has to do with reordering. We talked about reordering a lot. Well, one interesting fact is that if we reorder the system, then the ILU factorization changes. And it could be a better factorization or worse factorization, meaning the accuracy or its efficacy as a preconditioner changes. So we want to know which ordering is best. Is it going to be AMD, RCM, or natural? So those are 3 options. So these functions, ILU and BiCG stab, are available in MATLAB. So you can type help ILU, and the default, the simplest thing to do is the simplest thing that ILU does is to compute the incomplete factorization with 0 level of fill-in, so the 0 fill. Okay, so we talked about that, and that's what you're going to use. And if you have an older version of MATLAB, I think it's not called ILU, it's called IncLU for incomplete LU. Okay, and similarly for BiCG stab, there's help on how to use it, right? You pass it the matrix, you pass it the discretization of your right-hand side vector, right? You call it G or F. Pass it a tolerance. I guess we didn't specify a tolerance, but commonly 10 to the minus 6, some residual norm of 10 to the minus 6. I don't know if you talked about this in your class, in your part of the class. Like 10 to the minus 6 as a tolerance for when to stop the iterations. You might choose a maximum iterations. Make sure that this is large enough. Like you could choose maybe, depending on your problem size, 10,000 or something like that. And you could also pass in your preconditioner, your ILU preconditioner. And there are some examples down here of how to use it, right? So here it uses a diagonal preconditioner. Okay. And the things that you return are your approximate solution, a flag to say whether or not you have converged, and something about the residual. And you want to know if you have converged, how many iterations were taken by the different methods. So if more iterations were taken, then it was harder to solve or easier to solve. And you want to know which ordering for the precondition was better, which discretization was easier to solve with, etc. Okay? So any questions about this? Have you guys tried this already? Try to use these iterative solvers in MATLAB?
Yeah, I think Tommy did that.
Yeah.
First one.
Okay, excellent. So you guys know how to do this using CG, I assume, using PCG. So this time, our matrix, because there's a convection term, the matrix is non-symmetric, so we can't use CG. This is why we're going to use by CG stab instead. Okay? Okay, so are there any final questions?
So basically, you're explaining some kind of numerical experiments and rather than some theoretical.
Yeah, so it will be very hard to try to answer these things theoretically. If you can't, there are some things, you could take quite a few derivatives and you could see which of these discretizations might be better. That would be very interesting as well, as bonus maybe. But what I'm imagining primarily is experimental evaluation. And you could maybe try to make a hypothesis. Like who thinks that the original discretization is better? And who thinks that the new discretization is better? And you could make some kind of guess. Or who thinks that the discretizations are actually identical, right? And the answer may differ depending on the beta parameter, and it may even differ depending on the differential equation. This is just one, or maybe even the solution that you choose. But at least in this context, let's try to understand. I think it's a fun question. Try to understand which one is better.
So the first discretization we have it in conserved form, right?
This is true.
And in second discretization we have it in non-conserved form.
This is true.
So that will basically depend on problem to problem, right?
This is true. Now, that's a very good answer. That's a very good answer. And you can maybe probe a little bit more deeply. So maybe for this question, what do you think the answer will be? And maybe for another differential equation, like a differential equation that is based on a conservation law, right? Then the results could be different. And if you have time, since you know about this, you could try another one. Up to you. All right, so thank you very much. Have a nice weekend, and I'll see you on Monday.